Next up, we are going to have Intrinsic, which is our non-volatile memory company. So first we're going to see a video, and then I'm going to chat to the CEO, Mark.
So Intrinsic brings together two elements that are really important. So my research team at UCL have been working on this new technology for about 10 years or so now. And also in Mark Dickinson, a CEO who has a breadth and depth of experience in some of the UK's leading semiconductor companies, such as ARM and Imagination Technologies. So in my team at UCL, I'm a professor. I've been working on nanotechnology and nanomaterials for more than 25 years now. And I'm really pleased to be working with my co-founders, Adnan Mohonic, who's one of the UK's leading young researchers, and in fact the technology developed out of his PhD research, and Wing Ng, who's an extremely talented experimentalist and who's developed this technology in an academic environment using the clean rooms at the London Centre for Nanotechnology, and is now working very closely with our partners in IMEC to translate that technology into a more commercial fabrication facility. And then, of course, bringing Mark in as CEO brings a breadth and depth of experience in the semiconductor industry, which is so important because that's such a competitive industry and there's such high demands on any new technology that is trying to penetrate the semiconductor market and be accepted by the semiconductor industry. So the fact that he has this experience and he understands the market so well will really help Intrinsic to move forward at quite a pace. So this is a really exciting time, and I think the team are extremely strong.
Intrinsic is a spin-out of UCL working in the area of non-volatile memory. Non-volatile memory is used in almost all electronic products. It's called non-volatile because it retains the information stored even when the power is off. It is used for storing program code, as well as storing data such as the photos you take on your smartphone. Today's non-volatile memory is based on a technology called flash. However, flash has some serious issues. It is not very fast. It has limited endurance. But one of its biggest drawbacks is that it is very difficult to integrate on the same chip as the processor. Not being able to put the permanent program memory and the processor on the same chip significantly hampers the design of chips for many applications. This is especially true for one of today's fastest growing sectors, artificial intelligence, where high performance and low power consumption are critical. Intrinsic's technology, based on the patented invention of a new nanoscale non-volatile memory, will provide a much-needed solution to this problem.
For many decades, improvements in microelectronics have been achieved by transistor scaling and smart architectural solutions. However, with the aggressive increase in computing demands, we need to consider innovations at a more fundamental level. Intrinsic's innovation is a memristor, a novel nanoelectronic device. A memristor has a unique ability to react to external stimuli and dynamically change its resistance with superior energy efficiency. We have developed an excellent memory technology by using the resistance to store data. To make our memristors, we use silicon oxide, the most used, the most understood, and the cheapest material in the whole microelectronic industry. This makes our memristors extremely simple and also easy to integrate with existing chips. Current non-volatile memory technologies are not easy to integrate, and our technology is solving this critical challenge.
What we are building is called a resistance switching memory. The building block of this memory element consists of an active memory thin film material sandwiched between two metallic-like electrodes. Using state-of-the-art thin film deposition techniques in our laboratory and our patented technologies, we are able to engineer this active memory layer with the right composition and optimize its electrical and physical characteristics for resistance switching. We couple this layer with matching electrode material, and this combination enables us to build prototypes of our memory device with performance comparable with industry-leading metrics in terms of low voltage operation, excellent endurance, retention, and temperature performances. And whilst we are pushing the boundaries on our device performance, It is critical that our material choice and device structure are fully compatible with global semiconductor manufacturing infrastructure. This is to ensure that the process we develop in our laboratory can be transferred for large volume manufacturing.
What is next for Intrinsic? We are currently working to complete the transfer of our technology from the lab to a commercial manufacturing facility. This will demonstrate that our innovative devices can be fabricated using standard manufacturing techniques. The next step, requiring further investment that we aim to close before the end of the year, will be to build more sophisticated test chips. This will include bigger memory arrays and other functionality such as processors on the same chip. These devices will show the simple integration, the high performance and the low power consumption of our unique technology. Also, we will be building the electronic design automation tools that will be used by chip designers to integrate our memory technology. By using an industry standard design flow, we put the ability to use our technology into the hands of any designer that wants to benefit from it. Today, non-volatile memory is a $60 billion market which continues to grow. Given the huge demand for this type of memory, I'm convinced that Intrinsic will become a significant player in the global semiconductor industry.
Hi, Mark. Welcome to the showcase.
Thank you, David. Hello.
Excellent, and great to see the video there. Everyone that I've been speaking to in the industry, and when we were doing our due diligence, was super excited about the idea of being able to co-locate non-volatile memory with processing logic. Can you tell me a little bit more about why that's so exciting, and also why it's so hard to do? Why Intrinsic able to do this when others can't?
Yes, so many people who work in the sort of compute or semiconductor industry will have heard of what's called the memory bottleneck, which is basically any processor that's doing work needs to get its data, both in terms of the program and the data it's working on, from somewhere. And typically that is stored in what's called non-volatile memory. In other words, a persistent memory that remembers forever, even if the power's not there. We use it all the time in our smartphones, we use it in our cameras. The problem we have is that to get the best performance, you want that memory to be as close as possible to the processor. Moving memory, moving data takes energy, takes time, kills performance, kills power consumption. And with today's technologies, today's non-volatile memory technologies, you just can't do that. You can't produce a high-end, if you like, advanced processor and put right next to it this non-volatile memory. So that's the exciting thing, because Intrinsic can do just that. We can bring that memory close to the processor. And one of the main applications where that is particularly pertinent or particularly exciting is in AI. And we've just heard a lot about AI applications, and we're going to see that these vast models that people build in order to do AI functionality requires storage. That model needs to be stored, and it needs to be stored in something that's non-volatile. And so Intrinsic can enable that type of, if you like, that capability. Why is it so hard? Well, one of the problems with, first of all, there are two problems with memory. One is you want it to be very, very dense. You want to have as much memory capacity as you can in a small an area. That means building memory components, things that you can detect at nanoscale, in order to be able to pack them in as densely as we can. So first of all, you've got a challenge, which is you're trying to make something extremely small, which remembers stuff. The particular challenge we've got, though, is that not only we want to do that, but we want to do it using processes and materials that are already being used in the semiconductor processing. We can't come along with some new material and say, oh, this remembers very well, because it's going to contaminate the process that people are using to build the chips in the first place. And that whole infrastructure, if you like, to build a chip is unbelievably complex, unbelievably difficult to change. So adding anything new into the formula to build your next Intel processor or Apple processor is an extremely challenging thing to do. But what we've done is combine both this nanoscale problem, finding something that remembers, with building it out of materials that are already in the fabs that make the Apple chips and the Intel chips and all the other chips in the world.
Great. And you've already got wafers back from commercial fabrication units that have made successful wafers. You're showing incredible amount of development this year. What are the plans for the rest of this year?
So yes, we've got wafers back already. Basically, we're moving the stack from something that's been developed in the lab, as you saw in the videos, to something that that's being built in a commercial style fabrication. Our initial steps are to take what we've done, replicate it in the fab, and that's what we're doing right now. And as you say, that's going very well. It's going to plan, and the results we've got back so far have been extremely encouraging, very good, in fact. What we need to do now is take that and build, if you like, smaller devices and more of them, because that's effectively what we need to be able to show that we can do. We need to be able to make, show the devices can be made very small, and we need to show that they can be made in very large arrays. That will be a process over time as we sort of push and push and push and take it further. But the first step, this year we hope to get small arrays, and then with further funding, we'll be able to build much bigger arrays as the next stage of our development.
And this is a technology which I know you're starting off thinking about microcontroller units because they have a particular use for this process and memory being integrated together. But this is a technology that could be a sort of ubiquitous memory. I mean, how big can this be?
Well, huge, enormous. We've got a very clear market that we can go after because it's already there. It's a market which uses non-volatile memory integrated today. It's a market which has to live with some very difficult technology challenges because it's using old technology. We can't move it forward. First of all, we want to liberate that market. We want to take that market which already exists and say, here's a better version of what you're using. It makes it very easy for us because the value proposition and the sales process, if you like, is simple, and the market exists. But having proved the point, if you like, there are a vast number of opportunities. Almost every chip in the world could benefit from having this non-volatile memory on the same device. I talked a little bit about AI being one of the very interesting areas today where you can easily see why that's the case. You need this vast amount of model data memory, and you need it close to the processing elements. And as we push AI out into all the edges of our sort of world, we want that to be as low power as possible. We really want it to be able to be fueled from a very small Bramble fuel cell, implementing the algorithms from Human Loop, and all doing that on a very, very small amount of power. So there's this huge opportunity, I think, to transform what you can do in semiconductors, as well as actually sort of supporting, if you like, the traditional way that semiconductors are used already.
Brilliant. And you're looking later in the year to raise funding to move down to that kind of millions of devices level at the fab. So you'd welcome contact from anyone watching this who would be.
Yeah, of course, yes. Yeah, absolutely. Yeah, I mean, this is we're delighted that we've got to the point now where we're funding, if you like, access into these commercial fabs is extremely expensive. So we're very pleased that we've got that step going, and the results are going very well. But to continue that, we're going to need more funding to push out those the test chips, if you like. So absolutely, we're looking for help in that journey.
Brilliant. Well, look, thank you so much for joining today. It's been a delight to watch Intrinsic's development, see all these wafers coming back that are working from the fab, and just seeing the excitement build around this technology. So looking forward to the next year of the journey with you.
Okay, yeah, likewise. Thank you, David.
Brilliant.